Thank you all for coming. My name is Tiffany Kasanicky, and I'm a software architect at Intel in the data center group. And my team develops the management software for Intel persistent memory based on the 3D XPoint DIMMs. I've been at Intel for almost 20 years now, and there's a lot of things that I really like about Intel. But probably my favorite is sabbatical. So, show of hands, how many people like having time off from work? Right, okay. Yeah, one honest guy. The reason I'm telling you this is because literally the last thing I had to do before I went on sabbatical in August was put these slides together for this talk. So, my guess is that I was under the impression that I was somewhat funny, which I'm not at all. Because when I returned from sabbatical, you can't hear me? Let's see if I can get this closer. Is that better?
You're talking to your shoulder.
Hello. I opened up my slides, and what did I find? Why, yes, the title of this talk is Managing Persistent Memory. Therefore, the agenda must be 1, managing, followed by 2, persistent memory. Back to basics, people. So, what is persistent memory? Persistent memory is an emerging technology in which non-volatile DIMMs are placed on the memory bus. They can be used alongside of or in place of existing volatile memory DIMMs like DRAM. The thing that differentiates non-volatile DIMMs from volatile memory DIMMs is the data that's stored on them is retained when the power is lost or the system is shut down. Therefore, they can be used as a form of permanent storage, like hard disk drives and solid-state drives. For the purposes of this talk, the hardware implementation of the non-volatile DIMMs is irrelevant. What matters is that the DIMMs are on the memory bus and that they're non-volatile. So then, why do we need to manage them? I mean, we don't really manage our memory, our DRAM DIMMs, other than to determine how much is there and how much we're using. Well, persistent memory and non-volatile DIMMs fall in this sort of in-between space where the existing paradigms of memory, which we don't manage, and storage, which we do manage, overlap. For example, non-volatile DIMMs, as they're named, generally have some form of non-volatile media, which means that they have a controller on them and they have firmware, which has to train the media and manage it over time. And what this means is that firmware, although we all write perfect code all the time, may need to be updated every now and then. Therefore, we need some sort of a software stack that's in charge of or administering or dealing with the persistent memory on non-volatile DIMMs. Now, I've tried to make this presentation geared toward the standard interfaces for managing persistent memory, but I will spend a few minutes at the end talking about this software stack that Intel developed for managing persistent memory. So let's start with the big picture. This diagram, it comes in many forms, but it basically represents the high-level overview of the software stack for persistent memory. You'll notice that there's 3 underlying usages. The 2 on the right, block and persistent memory, are how applications actually use the persistent memory. In block mode, an NVDIMM driver presents a standard block storage interface to applications, so they don't need to be modified. They can access persistent memory in the same way they would an SSD or hard drive. The more interesting usage, however, is on the right, where persistent memory is mapped into the system physical address space. And a PM-aware file system allows applications to open a file and memory map it, giving applications direct load store access to a mapped area of persistent memory from user space. This completely bypasses the kernel, so no context switching, no page caching, and gives applications the shortest code path to persistence. However, this requires that applications are re-architected to understand persistent memory using the persistent memory programming model. And this is where NVML comes in. NVML is a framework of libraries that make persistent memory programming easier for applications. Well, these two underlying usages, block mode and persistent memory mode, are actually the reason that we do this stuff. It's not the focus of this talk. There's a lot of good information on the link there at pmem.io where you can learn about NVML and persistent memory programming model. Rather, the focus of this talk is on the third usage model, the software components that are necessary to set up, monitor, and maintain the persistent memory on the non-volatile DIMMs. In this diagram, I'm showing two different software components, one in user space and one in the pre-boot UEFI environment. In order to manage persistent memory, we need to start with the ability to do a few key things. First, we need to be able to discover the physical non-volatile DIMMs and be able to communicate with the firmware on them in order to control them or administer them or make them do things. And second, we need to be able to discover the logical regions of mapped persistent memory in the system physical address space and surface them to user space. So the first step in discovery of both the physical non-volatile DIMMs and the logical persistent memory regions is through the NVDIMM firmware interface table, or NFIT for short. The NFIT is an ACPI system description table which is created during BIOS initialization to describe the NVDIMM topology. Prior to the NFIT, there was no method to describe the unique characteristics of non-volatile DIMMs from the BIOS to the operating system. Therefore, the NFIT was developed and standardized in the ACPI spec, starting with version 6.0, in order to provide a firmware agnostic method or solution for enumerating and configuring non-volatile DIMMs. In the NFIT, NVDIMMs are represented by 0 or more NVDIMM devices under a single NVDIMM root device in the ACPI namespace. This allows software to enumerate the NVDIMMs present in the platform and associate their system address ranges created by the NVDIMMs. Software evaluates the NFIT during initialization, and any changes to the NVDIMM state at runtime or information regarding hot-added NVDIMMs is communicated through the FIT method of the root device. The NFIT is really a collection of 7 different structures linked by indexes and device handles. So in discovering NVDIMMs, we start with the NFIT region mapping structure. If the NFIT had a heart, this would be it. As you can see from the number of lines emanating from it, it connects basically all the other structures together. The region mapping structure describes the NVDIMM regions and associates them to SPA ranges, associates them to control regions, their interleaves, the flush-in addresses, and the associated SMBIOS tables. The region mapping structure also contains the NFIT device handle, which is how we enumerate NVDIMMs and how we execute functions on them. And we'll talk a little bit more about that in a minute. Cleverly enough, this device handle also describes the physical NVDIMM topology. So it is actually made up of the CPU that it's connected to, the memory controller that it's connected to, and the channel within that memory controller. Now, each physical NVDIMM will have one or more region mapping structures. For example, it might have a control region structure, which describes how to communicate with it, and one or more persistent memory SPA region structures. The NVDIMM control region structure, as I just mentioned, is linked to the region mapping structure by an index. Now, this structure describes NVDIMM function interfaces and, if applicable, any of their block control windows. It also has attributes that allow device drivers to determine whether or not they can support them. So it has vendor ID and device ID and subsystem vendor ID and device ID, and attributes which describe how to uniquely identify an NVDIMM, such as the serial number and the manufacturing information. The ACPI spec actually specifies how you're supposed to identify NVDIMMs both in software and on the label, interestingly enough, which is a combination of vendor ID and manufacturer and serial number. Now, the control region structure also contains an interface format code. Because an NVDIMM can be a combination device consisting of different regions types, for example, persistent memory and block, a region format interface code indicates the region type as well as the specific implementation within that type. This allows for variability across vendors as well as within vendor offerings, and allows for loading drivers for managing the DIMM as well as handling the different address ranges supported by the DIMM. In other words, the interface format code allows us to load generic drivers like a PMEM driver or a block driver, as well as vendor-specific drivers for the same DIMM. So the control region structure gives us a bunch of information about the physical NVDIMM and how to identify it. We can also gather more physical attributes of the DIMM from the associated SMBIOS tables, in particular the type 17 memory device table. What's not shown in this diagram is that the region mapping structure actually links to the SMBIOS tables because it contains the SMBIOS physical ID of the DIMM. So the type 17 memory device table also gives us things like the size of the DIMM, the form factor, the device locator and bank locator of where the DIMM is located on the board. And together with the control region structure, this basically rounds out all of the information we need about the physical NVDIMM itself. Oops. Let's go back one. So next we look to the system physical address range structure, or SPA range structure, which allows us to enumerate the logical mapped memory associated with an NVDIMM. The SPA range structure is again index linked to the region mapping structure. The difference between the two is that the SPA range structure is could be from multiple DIMMs, whereas the NVDIMM region mapping structure is for a single NVDIMM. So you could have one SPA range structure associated to many NVDIMM region mapping structures if the capacity was interleaved. The SPA range structure contains attributes about the memory type, like the memory attributes, proximity domain, the base address, and the length. Enumerating the SPA range structures gives us the ability to discover the mapped regions of persistent memory. Next, the interleave structure basically does exactly what it says. It describes the interleave options for a particular NVDIMM region. It also allows us to convert between device physical addresses and system physical addresses. And the flush hint address structure describes special physical addresses that, when written to, help cause the data to be flushed out from the memory controller to the persistent media. And finally, the block data window region structure describes the block data windows for an NVDIMM, if they have any. This would be the case if, like, the control regions of the DIMM are not mapped into the system physical address space. You communicate with them via block mechanisms. So as you can see, without needing to communicate with the DIMMs at all, just by simply reading the ACPI NFIT table, we can do some of our key management requirements. We can discover the physical NVDIMMs and their attributes, and we can discover the logical regions of mapped persistent memory and their attributes. However, in order to really administer or be in control of the DIMMs, we need to have some form of communication mechanism with the firmware itself. Now, drivers can implement this directly. They can call firmware control interfaces, which are described in the NFIT. However, this is highly vendor and firmware specific. Therefore, the platform firmware BIOS also helps us abstract this communication mechanism by implementing what's called device-specific methods, or DSM. A DSM is an ACPI control method that provides a device-specific function that is consumed by a device driver. The DSM interface is available after handoff to the boot device services in UEFI. And it basically looks like this. A device driver in the kernel space would call a DSM. That's BIOS ASL code, which then goes into SMM mode. The BIOS would build the firmware mailbox command, send the command down. The firmware would complete the command and send back information. The BIOS would exit SMM mode and return the payload back up to the device driver. With ACPI spec 6.2, we've got some standard DSMs for the NVDIMM root device. So this would be mainly controlling system scope level functionality for all the NVDIMMs in the platform, such as address range scrub. ARS, or address range scrub, allows the platform to communicate memory errors to the system software, which will allow the software to prevent access to addresses with uncorrectable errors. So we have functions to query the capabilities of the address range scrub to see if it's supported and its system-wide attributes. We have capability to determine if an address range scrub is in progress and to start a new one if it's not. And also to clear uncorrectable errors and test the flows using injection. There are also many device-specific DSMs, which are associated with the interface format code. For the most part, the device-specific DSMs are not yet standardized. So this is an example of the DSMs that are implemented by type interface format code 201.301 DSMs, which is the Intel DIMMs for non-energy backed byte addressable persistent memory and block. So you can see here we have DSMs for monitoring the DIMMs, get smart health, get smart thresholds, set smart thresholds. We have DSMs for communicating with the DIMM, so send a pass-through command, determine how that command affects me using the get command effect log. And we have DSMs for maintaining the DIMM, like firmware update, and then test inject error. So now we can discover the DIMMs. We can discover the persistent memory associated with them. We can communicate with the firmware on the DIMMs to set them up and to manage them. The last thing on our list was to be able to surface the persistent memory to user space. To do this, we need a driver stack in the kernel. Since this is highly operating system specific, we're going to go through both Windows and Linux. So this is a diagram that I stole from Dan Williams at Intel, which represents the Linux NVDIMM subsystem. The libNVDIMM subsystem defines a kernel device model and control message interface for platform NVDIMM resources. It provides support for 3 types of devices: PMEM devices, block devices, and NVDIMM devices that support both simultaneously. So for each type of access method, libNVDIMM provides a device driver: a PMEM device driver, which drives a system physical address range, and a block driver, which drives I/O using a set of platform-defined apertures, which is specific to just one DIMM. Direct access to persistent memory is provided by DAX file system extensions to bypass the page cache and block layer to mmap persistent memory from a persistent memory device directly into a process user space. ND control on the left is a utility for managing the libNVDIMM subsystem, such as provisioning the capacity, enumerating devices and regions, and providing a management interface for user space. The Windows operating system refers to their NVDIMM architecture as storage class memory, or SCM. I borrowed parts of this diagram basically directly from MSDN. You can see the link there. While Windows is very similar to Linux, they also have a few minor differences. They have a bus driver included in the Windows OS for SCM, and then they have a disk driver per persistent memory namespace and an NVDIMM driver instance per DIMM. So while Linux has one instance for the that handles all the regions, Windows has one instance per namespace. So the SCM disk driver handles the I/O to the persistent memory, and the physical NVDIMM driver is used solely for management. Microsoft also implemented DAX functionality in NTFS to support persistent memory file system. So just a few minor differences between the two. So those were the high-level software components for each operating system in the kernel, but how do we actually surface the persistent memory to something that an application can consume? So let's walk through an example. If you remember from the NFIT, we start with the region mapping structure, the heart of the NFIT. So this is a diagram showing 4 NVDIMMs. Each DIMM has one persistent memory region. That would be an NVDIMM region mapping structure. The second DIMM has 2. The PM regions can be combined to make a contiguous system physical address range when they are interleaved. We call this an interleave set. In an interleave set, accesses are sent from the CPU to the NVDIMMs based on their address. An interleave set could be one-way or two-way or four-way, which is what this example is showing, where way is the number of DIMMs contributing to the interleave set. Actually, there's 2 interleave sets here, one one-way and one four-way. Interleave sets can include some fairly complex math and attributes such as memory controller mirroring between the interleave sets. Interleave sets or SPA ranges can be further subdivided into namespaces, and actually they cannot be accessed without first allocating them to a namespace. So just as an NVMe SSD can be carved into namespaces, NVDIMM namespaces are very much the same idea. A namespace defines a contiguously address range of non-volatile memory. They represent the unit of persistent memory storage that appears as a disk or a /dev entry that applications can use for I/O. Namespaces are not to be confused with other subdivision mechanisms like disk partitions or virtual volumes that are implemented by software RAID stacks. These things still exist on top of namespaces, just as they do on top of any other direct attached storage. Persistent memory namespaces are associated with an interleave set. Namespaces are defined by labels, which are stored in the label storage area, or LSA, on an NVDIMM. The label storage area is a region in the persistent memory metadata of the DIMM. The label storage area contains a header called the index block, which appears twice at the top of the label storage area. This provides a power-fail-safe method for updating the information in the LSA by alternating between the 2 index blocks when writing. The index blocks contain a bitmap which indicates which labels are in use and which are free. So following the index block is the array for storing the actual namespace labels. A namespace is described by one or more namespace labels. The label is the metadata that's stored in the LSA, and it describes the attributes of the namespace, such as the name, which interleave set it's associated with, the type of namespace it is, and whether or not it has a BTT, or block translation table, for providing power-fail-safe atomicity. Namespaces can be local, which means they're limited to a single DIMM, such as namespace 2 in this picture, or non-local, which means they're associated with more than one DIMM. such as namespace 0 and namespace 1. In the case of non-local namespaces, the number of labels is equal to the number of DIMMs contributing to the interleave set or the SPA range. In this case, there would be 4 namespace labels for namespace 0 and namespace 1, one on each DIMM. And all of them have to be there for the namespace to be good. So in using the NFIT, we can discover and enumerate the physical NVDIMMs and the logical persistent memory regions. Using DSMs or direct communication with the firmware, we can communicate with the DIMM and make it do stuff. And with namespaces, we can now surface persistent memory to applications and user space. So putting this all back together, I'm going to walk through an example of the management software that we created for Intel persistent memory DIMMs. As I mentioned before, we have 2 different management components, one for user space and one for the pre-boot environment. They both support generally the same functionality. This is the high-level architecture of the UEFI management software for Intel persistent memory. Currently, our UEFI software is implemented as a monolithic driver based on the NFIT that manages all the Intel NVDIMMs as well as the I/O to the DIMMs. In the UEFI stack, we also have a command line interface that plugs into the UEFI shell and an HII interface which plugs into the platform BIOS menu. As I said, the driver supports both management and I/O to enable booting to a persistent memory namespace. So our UEFI software basically gives us 2 things. It gives us the ability to manage DIMMs in a pre-boot environment when we don't support the operating system, as well as it allows us to boot to persistent memory namespaces. Right now, the protocols that our driver supports are for our own internal use for the most part. We do have some standard UEFI protocols implemented by the driver in order to do things like firmware management and security and block I/O. One thing to note about the UEFI software is that, if you recall, the DSM interface is not available until after handoff to the boot services in UEFI. So it's actually not available for use by our UEFI software. The driver handles communicating with the firmware mailboxes directly. Now, I suspect this is just our 1.0 version of the UEFI software, but a good portion of this will probably be re-architected at some point to be more standardized and put into the UDK to look a lot more like either the Windows or the Linux stack, where you have a generic PMEM driver, a generic bus driver, and then vendor-specific management drivers. So I'd stay tuned for that in the next couple of years. Now, this is the high-level architecture for the user space management software. We call this IXPDIMM software right now. We developed the management software with the philosophy of augmenting rather than replacing existing storage management software stacks. Therefore, a lot of it is built around industry standard interfaces. So similar to UEFI, we have a command line tool which gives us end user access and manufacturing support that runs in the OS shell. The syntax of both CLIs, the UEFI and the operating system CLI, follow the DMTF server management command line protocol for the most part. And then to enable third-party tool integration, as well as to provide remote access, we have a Common Information Model, or SIM provider library that plugs into WMI and Pegasus and SFCB. Intel worked with both DMTF and SNIA to extend the SIM standards to support NVDIMMs and persistent memory. For programmatic access, we have a native API library. And then finally, to monitor the DIMMs, we have a system service, or daemon, which captures events to the system event log. The OS software is implemented using an adapter pattern, which abstracts communication. Oops, where did my mouse go? Sorry. we use an adapter pattern to abstract communication downward to the underlying OS components. As you can see, we have basically 4 adapters, one for Linux, one for ESX, one for Windows, and one that's a simulated adapter. So this allows for the majority of the management software stack to be independent of the underlying dependencies. It also gives us the ability to test all of the management software using a simulator. So IXPDIMM software, the user space management software, is currently open sourced with a very flexible 3-clause BSD license. It's also included in the latest Linux distributions and on track to be in the next versions. The UEFI software is included in Intel's memory reference code, so their BIOS. And as I said before, I think we're, in the next couple of years, looking to move more and more of that UEFI software into the UDK for future versions. So the OS software, I've put the repositories up here on GitHub, is broken down into 2 pieces. One is the vendor-specific Intel DIMM software, and then we also have some framework libraries for the SMCLP, CLI syntax, parsing, and the SIMOM integration with WMI and Pegasus and SFCB. And that's the frameworks. So in summary, we need management software in order to set up, monitor, and maintain the persistent memory on non-volatile DIMMs. We need to be able to discover the non-volatile DIMMs. We need to be able to identify them. We need to be able to discover their capabilities. We need to be able to provision them so their capacity gets interleaved into system physical address ranges. We need to be able to manage namespaces. We also have a lot of standard disk-like functionality, like monitoring sensors, updating firmware, and checking the performance. And we do this utilizing the NFIT, which gives us the ability to discover the physical NVDIMMs and the logical PM regions. We can communicate with the firmware using the DSM mechanism in order to provision the DIMMs and monitor them. And then using the namespace labels, we're able to surface the persistent memory to applications in user space. So I hope you've learned just a little bit about managing persistent memory. We should have plenty of time for questions. I really want to thank you for listening.